Yo, today's problem is a direct recommendation from my absolutely favorite subscriber. His name is SD. That stands for something delightful, super duper, South Dakota, sassy degenerate, some dude. I'm not sure what it stands for, but it stands for the subscriber, duh. So we're gonna go through this problem that he recommended, and this is a glorious problem. So I really appreciate the recommendation. I struggled too solving this, but I thought about it a little bit. Um, and this is a beautiful problem. So thank you again just for recommending, and let's get right into it. Okay, so problem 1203, sort items by groups and the respecting dependencies. Okay, so there are n items, each belonging to 0 or 1 of m groups, where group I is the group of the ith item that the ith item belongs to, and it equals -1 if the ith item belongs to no group. Okay, so we have all these people, or not people, we have all these items, and these items are associated with certain groups. Okay, and those items are within one group. So one way I guess you could think about this is that there's these like boxes, and this is group A's box, and there's another box, and this is group B box, and each item, like item 1, could be in group A, could be in group B, or it could be -1 and it's alone, and it's, you can think of it as its own group, right? It has its own exclusive group just for it because it doesn't associate with any other group. Okay, a group can have no item belonging to it. Okay, so it's possible that you created, there's a group that exists but no item is in that box, which is the group. Okay, return a sorted list of items such that the items that belong to the same group are next to each other in a sorted list, and that there are some relation between these items where before items I is a list containing all the items that should come before the ith item in the sorted array to the left of the ith item. Okay, so when I look at this, right, this second bullet point should be very familiar, right? This first one, not so much. This first one is kind of introducing some new idea, which is tricky. But if we were to look at this problem and say, if we were exclusively solving for this second bullet point, this reminds me a lot of the prerequisite problem, where you have classes, and then there's prerequisites for that class, and you need to find a valid order of classes that you can take, right? Because you have to take the prerequisites before you take the classes after. So that's what this before items I kind of reminds me of, right? Because before items I, at I equals some array, right? J, K, L. And what that basically means is you have to go through J and K and L before you go to I. So if we were thinking that as in a graph in terms of like prerequisites, I guess another way you could do it is like say before items. Now, of course, this isn't this isn't the problem, but I'm just trying to give you an example of something that is similar that you probably solved before. Before items, before calculus, right? Before you take calculus, you have to take what? It's been a little bit of time since I've taken calculus. You need to take algebra 2 and geometry. I don't know. Right? So before you take calculus, you need to take algebra 2 to learn about algebra and basic arithmetic, and geometry to learn spatial reasoning and graphing or whatever. And that's how you can take calculus. So before you take the calculus course, you better take these prerequisites. And if we modeled that using a graph, right, we would have these nodes where it was algebra 2 and geometry, and these nodes would point to calculus, right? And in the case of before items JKL, well, you just have it that You have these nodes, J, K, and L. And they all point to I. Okay? So this before items idea should be very familiar. And the approach we use to solve this kind of system where you have these relationships in a directed graph where you have to take something before you take something else is topological sort, right? Topological sort is the solution that you use to find a valid ordering of these nodes such that you don't break any of the prerequisite relationships. Okay, so you're going to return any solution if there's more than one solution, and return an empty list if there is no solution. Okay, so what would it mean for there to be no solution in this kind of problem? Well, that would mean there's a loop, right? Because say like you had a system where, you know, the college counselor gave you this, it's like, okay, you want to take calculus? Well, you need to take algebra 2 and geometry. It would be really backwards if maybe before you took geometry you had to take like arithmetic. I don't know. And now we're going too far back. Yeah, so you're like, okay, I need to take algebra 2 and I can take algebra 2 with arithmetic, and then I'll take geometry, and then I'll take calculus. But then what if he told you, oh, but you also need a arithmetic. So maybe you go up, so imagine he gives you this prerequisite list, right? You're going to be like, okay, well, I guess I'll start at arithmetic. And he goes, no, you can't take arithmetic because you need to take calculus. So you're like, okay, I'll take calculus. He's like, you can't take calculus till you take algebra 2. So you're like, okay, I'll take algebra 2. And he's like, okay, there's no prerequisites for that, so you can take algebra 2. But you also need to take geometry before you take calculus. You're like, okay, then I'll take geometry this semester in algebra 2. He's like, no, you can't take geometry until you take arithmetic. Notice how this is a problem? Well, you can't take arithmetic until you take calculus. So now you have this infinite loop. You can never start because there's this cycle, so where do you begin? Right? There's always a prerequisite in a cycle, right? There's always a prerequisite for any node inside of that cycle. So this is a problem. So an empty list would mean that you have a system where there's a cycle in the topological sort, at least in the before situation, right? Covering this bullet point, because we haven't even addressed this first bullet point. But certainly in this problem, we're going to need to do some sort of topological sort ordering. So we might as well write the code that does that before we continue the problem. I'm just going to note that I'm not going to go through why the following code solves topological sorting. There's a plethora of videos. This is really just the algorithm to carry out topological sorting efficiently. And you can think about it, maybe if there's some time at the end, or if you write in the comments, hey, could you further explain how this works? I don't understand exactly how topological sorting works. Then maybe we can address it then. But this problem is really long, so I don't want to focus too much on that aspect, because I imagine that you probably understand topological sort to a certain degree if you're doing this problem. So when you topological sort, right, you're going to take this graph that we built and the number of nodes in the graph. And there's a stack and there's a C array. The stack is initially empty. The stack is what you're going to use to fill up with the values in the order in which you can traverse this graph without breaking the topological sort ordering. And then you have this connected thing to reference what you've seen, if something's on the stack, if it's already been visited, yada, 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 okay? And like most of the things you can see, we're going to use DFS on a node U. If C of U, that means that this node has either been traversed already, or it's already been visited, or it's still on the stack. Then you return C of U equals 2. Otherwise, you're going to traverse this node. This is valid. Well, you're going to look at all the neighbors of this node, right? So you're going to look at all the neighbors V. And we'll just say if if not all DFS of V for V and G of U, so the neighbors of U. So if they don't all return true, that means this has a cycle and will return false. Otherwise, there's not a cycle, and we'll say we're done. We visited this node. We've looked at all of its neighbors, and since it's recursive, we looked at its neighbors' neighbors, and so on and so forth. And then we'll add this node to the stack, which will be kind of a marking. Okay, we can traverse this node next. And then since it got this far, it must have worked. So we'll return true. And then here we'll look at each node in the range n, because those are all the nodes. The reason why this is okay is because we're starting with a 0 indexed array. So I'm just looking at the items based on their index, right? This is item 0, item 1, item 2, item 3, item 4, right? If you're given n equals 8, you have 0 through 7. So I can just look at all 8 items this way. I'll run DFS on the item. And if it doesn't turn out true, that means it found a cycle starting at this node. So we return false. Or no, we'll turn an empty array. Empty meaning that there's no valid topological sort ordering for this node. Otherwise, if we get to the end, we'll return the stack in reverse. This is a confusing idea, but I'd say run a couple examples of this algorithm, just step by step, writing it down, and you'll see why you reverse it. Basically, I'm not going to get too deep into it, but there's a couple ways you can do this. Convince yourself with a few examples and just accept that it's factual and say, okay, this makes sense. You could go through the actual theory and write an all-encompassing, thorough proof that proves that this works. Or you can just memorize the code and regurgitate it and focus on the other aspects of the problem because you've memorized exactly how to write this. And I'm somewhat between 1 and 3, right? I'm not a mathematician and I'm not that intelligent. So it's okay if you don't exactly prove it to yourself that something works, as long as you know someone else did and you can just regurgitate that code. Okay. So this is how you topological sort a system. Now, what I'm also going to do is just think about this problem as the prerequisite problem and not even consider this group idea yet. So how would that work in this system? Well, you'd create a graph, right? We'll call it item graph. And there's n nodes, right? Because each item, there's n items, right? And then how would we build this graph? Well, we would look at each item and the items that come before it and enumerate before items, right? Because the way that this is given, this is saying node u, when u is 0, so node 0 has no before items. Node 1 has before item 6. Node 2 has before items 5. Node 3 has before items 6. Node 4 has before items 3 and 6, right? We would look at this, and then we would look at each neighbor, or maybe this would be v in before, and then u in before, right? So for a node, 0, 1, 2, 3, 4, 5, 6, 7, and the thing that comes before it, for each node that comes before it, in our graph, that node u would then have the neighbor v, right? Like, if we're looking at this example here, right, we have node 0, 1, 2, 3, 4, right? So node 4, when v equals 4, we'll have before equals 3, 6, right? So v equals 4, before equals 3, 6, because we did enumerate. So 0, 1, 2, 3, 4, and then 3, 6, before is 3, 6. U will equal 3, and then we'll say, okay, now there's this neighbor relationship from 3 to 4, and then u will be 6, okay, and there's this neighbor relationships from 6 to 4. Right, and that makes sense, right? Because before 4 has to be 3 and 6. So before 4 in our DAG, we have 3 and 6. Perfect. All right, let's continue. Going down this route of prerequisite building. So then after you do that, we'd say, okay, well then the items ordered is running topological sort on the graph that we just created. We call that item graph. And how many nodes are there? Well, there's n nodes. So let's just make sure that runs without error. Oh, I called it G instead of item graph. Oh, my computer is starting to get hot. Damn it. All right. And then let's go ahead and print item ordered, just to make sure that this system makes sense, right? We should have 6 before 1, 5 before 2. So let's see if all the constraints are met using this graph, right? So let's actually go ahead and build this graph from the system. So we have 6 before 1. So we have 6 before 1. We have 5 before 2, 5 before 2. We have 6 before 3, okay, 6 before 3. We have 3 and 6 before 4. So we have 3 and 6 before 4. And then we have 5 node, 6 node, and 7 node with no constraints. So is this order valid? Well, this is saying we go 6 first, and then we can take 3, and then we can take 4, and then 1, and then 5, 2, I forgot to draw 0, and 7. And that makes sense, right? Like this relationship works, right? Like all the constraints are met, right? Like 6 comes before 3 and 4, okay, that's good. 3 comes before 4, okay, that's good. 1 comes after 6, okay, that's good. 5 comes before 2, okay, that's good. 7 doesn't matter, 0 doesn't matter. So this system, this topological sort, to me, at least it looks good enough that it works. So in terms of just the prerequisite aspect of the problem, our solution is good, but we still need to encapsulate this idea of groups, right? This first bullet point, okay? Well, notice that each of these items belong to a group, right? Just like I said before, there's these boxes where things are going to go. So if we looked at this problem and we said, okay, well, item 0 is in group -1. So that means that item 0 is in a group all of its own, right? So if we had these items, so let's draw the items out. So we have, so we have item 0, item 1 through 7, okay. 2, 3, 4, 5, 6, 7. Okay. So we have these items all alone, and then we have these boxes. So we have this box 0 for these different groups. So we have group 0. We have group 1. And this says we have 2 groups, so we have 0 and 1. But then we also are going to have these additional groups that we have not yet defined for items that are alone, right? Because items that are alone are in their own box. So when we look at item 0, it's in group -1. So it's in its own group, so let's just call that group 2. And we move 0 over here, okay? It's in its own group alone. Item 1 is also in its own group, so we'll call that group 3 and put item 3 in here. Probably watching this right now like, what are you doing? Okay. We have item 2, which is in group 1. Okay, item 2 is in group 1. We have item 3, which is in group 0. Okay, item 3 is in group 0. We have item 4, which is in group 0. Okay, item 4 is in group 0. We have item 5 that's in group 1. We have item 5 that's in group 1. We have item 6, which is in group 0. And we have item 7, which is also in its own exclusive group. Everyone loves exclusion and status. The state of being a human being. And since it's also in its own group, we'll call that group 4. Okay? So this is the grouping order of all these systems, right? And within these boxes, right, it doesn't necessarily have to be 3, 4, and 6. But these things do have orders of nodes that they can be before and can't be before, right? Like item 1 has to be after item 6, right? So there's a contingency here that item 6 has to come before item 1, right? And item 5 has to be before item 2. and item 6 has to be before item 3. And item 3 and 6 have to be before item 4. And that's it. Well, one thing you'll notice is like, kind of the idea here is like, if you're in the same group with your friends, right, and you guys are all tight and you're always together, right? If one of your friends doesn't like somebody else, then you also can't like them, right? Because they're not a part of the gang. Meaning, if 3, 4, and 6 are in the same group and 6 has to come before 1, well, 3, 4, and 6 have to always be by each other. So that also means that 3, 4, and 6 have to come before 1. Does that make sense, right? Since 3, 4, and 6 have to be together and 6 has to come before 1, well, 3, 4, and 6 are a tight unit. So if 6 has to be before 1, then also this whole system here has to come before 1. So really there's a relationship where you have these, we'll call these new nodes, we'll redraw this system and say, well, since these nodes all have to be together, if you're in the same group, you have to be together. So if there's a before relationship between one of your nodes and another system, that affects all the nodes in the same system, right? Since there's a relationship between 6 and 1, that means there's a relationship between 4 and 1 and 3 and 1, right? Because if 6 is before 1, then the members that are the same group of 6, 3, and 4, they also have to be before 1 because they have to be together. I keep saying the same thing, but I want to make that point crystal clear. So what that basically means is that, well, then these things, these nodes, they're a tight unit. These nodes are a tight unit. Stalling, 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 stalling. And this has value 2, 3, 4. I can't count. 1, 2, 3, 4. Okay. So the reason why I can draw these new bigger nodes, or this is a hypergraph now, I can draw these bigger nodes because, well, there's contingencies between what? We said that 6 has to come before 1. So that means that 6 has to occur before 1 occurs. Right? So this is also a topological sorting problem, right? There's 2 topological sorting problems. There's a topological sorting problem between the nodes themselves, like there's topological sorting between 3, 4, and 6. There's a topological sorting between 2 and 5, right? And 1 and 7 and 0. But there's also a topological sorting order between the groups. So if we just took this system and we treated these all as hypernodes, right? So we'll call this group 0 and group 1 and group 2 and group 3 and group 4. If we found the order of this system, right? So like for this example, group 0 has to come before group 3. So a valid topological sorting order of this would be like here, and then this, and then this, and then this, and then this. So we do group 0, and then group 3, and then group 1, and then group 4, and then group 2. Right? So we know these are the order of the nodes that we need to traverse, of the groups we need to traverse, right? Because group 0 has to come before group 3 now, because 6 has to come before 1. Right? So there's a relationship in the system where, like I said before, if a member of your group has to come before a member of another group, that means your whole group has to come before the whole other group, right? Like, for example, if there was, now this isn't a part of this case, but I'm just saying for the sake that you understand, if there was a before 5 equaled 7 and 0, what would that mean? So think about that. Well, that would mean that, well, before 5, right, let's do it again like the other way. Before 5, 7, right? And before 5 is 0. Well, if 0 has to come before 5, and 5 and 2 always have to be together, that means 0 has to come before 5 and 2. Right? Because it can't split up 2 and 5 apart just to be behind 5. It has to be behind both of them. So that would mean then, well, then that would mean that the groups then have an issue. Right? There's an issue with these groups. So now we have this topological sort graph on the groups. So there's really two different kinds of edges here, right? If the edges in the before relationship come inside of the same group, it stays inside of the group's graph here. But if it's between groups, then it's an edge in the hypergraph, right? So like between 3 and 4, since they're in the same group, you only need to resolve that issue within the same group. But so then that gets added to the nodes graph. Now, if there's an issue with edges in different groups, right? If there's a before relationship between edges in different groups, that happens in the hypergraph. Okay? So let's get rid of this because it's confusing me. So what you can really do then is run DFS on the run topological sort on the groups, and then run topological sort on each of these smaller nodes, and then at the end connect them together, right? So when this was done, right, we got this ordering. Right, we got G0, G3, G1, G4, G2. That's just looking at the relationship between groups. And then we can replace G0 with the value of the topological sort on the nodes within group 0, right? So in order for 3, 4, and 6 to work, 6 has to happen before 3, which has to happen before 4. Right? So we would replace G0 with 6, 3, 4. Then we look at G3, it's just 1. So we'd run topological sort on that, and then it'd be 1. Then we look at G1. Okay, inside of that group, there's this ordering, 5, 2. And then we look at 6, 4. It's just 7. And then 6, 2 is just 0. Right, and that would be a valid ordering. So the idea is look at the groups of the nodes, find the edges that go between the groups, run topological sort to get the order of the groups, look at each group and get the topological sort of the nodes within that group, and then replace as such. We did here. Okay, so that's all I'm going to say about that. So let's go ahead and write the solution. So we have this item graph. Let's start here. So I'm going to do something a little hand wavy to make this a little cleaner. But let's not worry about that right now. So the problem is we can't have everything be group -1 because right when we look at this, you know, group 0 and 1 are in their own group, right? They're not in the same -1 group. They're in their own unique group. So every -1 group we can think of as its own unique group, which is its own unique vertice, right? 0 is a different vertice than 1. They're not in the same graph. So what we can do is we can just say, well, we'll say the group of something for each node. Let's set it to 0 times n. Ooh. So this is going to be the group of the node. And then we'll look at each node, or we'll call it item, and its group in enumerate group, right? Because item 0, it starts with this index, so it's the same kind of deal with as this v before thing. And then we'll say, or we'll just call it u. It's fine. So if group equals -1, we'll just use the value of m as a counter to notate how many actual groups there are, right? Because every time we encounter -1, that means there's an additional group. Right, so we'll say, okay, m, we'll say, okay, well then the group of u and m equals m and m plus 1. So we basically say, well, we know there is no group m because there's groups 0 through m minus 1. So we'll set the group of this one uniquely to m and then increment m by 1. That way, next time we encounter a -1 group, that one can be, the group that's assigned to that node is also unique. Otherwise, then the group is not -1, so it's one of the 0 through m minus 1 groups that are predefined. That would mean then that the group of u equals whatever this group value is. Okay, so now we properly have the group of each node. And now, well, we have to think about how this is going to work, because we have an item graph, and then we're also going to have this group graph, right? And how many nodes are in there? Well, how many vertices do we have in the group system, in the yellow system? Well, each group gets its own vertice. So there's m vertices. So then there's a group graph with a list like this, right? Because there's m vertices. Sorry. So there's m vertices. So the group graph is a for loop through the range m. All right. So where do we go from here? Well, some little trick we can do is, if we looked at this problem, right, well, we could right now go through this and run topological sort on the group, and we'd have to figure out if a node belongs to a group or it belongs to another group and how to connect it. It's going to get a little more complicated that way. So an easier way of doing this is say, well, we can run topological sort. Let's get back so we have something a little more clean, because this is a little crazy. How many times do I go back? Okay, so now we have this system, right? Which was the system where the red edges are the ones within a group and the yellow edges are between groups. We can also just keep, let's just say we kept this ordering as it was, right? Because 6 has to come before 1. And that's the only edge in here. Increasingly, we could find a valid topological sort disregarding the groups, right? So in this system, we could have 6, and then 3, and then 4, and then 1, and then 5, and then 2, and then 7, and then 0, right? So that would be a valid topological sort ordering, just looking at the topological sorting of the edges. I mean, just of the red connections, right? This would be a valid ordering. But let's do it a little bit differently. This would also be just looking at the red system. So disregarding the fact that there's yellow vertices, there's a yellow relationship, right? You could have 6, 5, and then 2, and then 0, and then 7, and then 1, and then 3, and then 4, right? That's also a valid ordering if you're not considering, right, the grouping, right? Because there's no red line that says that 5 has to come, that 4 has to come right after 6. It's just that 4 is after 6, right? So 4 has to be after 6. It doesn't have to be right after 6 or next to 6 or in the same group as 6, right? So just looking at the red connections, this is a valid ordering of the system. That's the point I'm trying to get at. Okay? So you could do that. And then you could look at this and say, well, this is a valid order. So let's add these things to their appropriate groups in that order. So 6 is in group 0. So what if we then created these boxes again? I know, I love these boxes. So there's 4 boxes. Oh, wait. Started group 0, right? Okay, there's 5 boxes. So 0, 2, 3. Bad idea. Okay. So we have group 0, group 1, group 2, group 3, group 4. And then what if we looked at these things in order and then added them to their boxes? So you say, well, 6, what group is 6 in? 6 is in group 0. What group is 5 in? 5 is in group 1. What group is 2 in? 2 is in group 1. What group is 0 in? 0 is in group 2. What group is 7 in? 7 is in group 4. What group is 1 in? 1 is in group 3. What group is 3 in? 3 is in group 0. What group is 4 in? 4 is in group 0. Right? So what we basically did is, now with respect to the group, each group is sorted appropriately. Right? That's essentially what I did here. I can sort the system based on just the before relationship and then put them in their appropriate groups. And that way, now the cases where, although the groups might not be sorted, right? The within each group, the nodes within that group are now sorted, right? And this is just another way of instead going the other way and sorting the groups and then looking at each pair of nodes and then sorting those. In this approach, we sort all the nodes and then put them in order in their corresponding groups. That way, each group itself, the nodes within that group are sorted. So now that that's the case, we can item ordered equals topological sort item graph. And then now we need to create this graph, this hypergraph between the elements. So how do we create the group graph? Well, we can look at all of the same edges. And what does it mean? Why did we create this yellow edge, right? This yellow edge exists because there's a node from one group to another group, right? These red edges didn't create yellow edges because these are relationships between nodes in the same group, right? So since these nodes are in the same group, there is no additional edge that needs to be created in the hypergraph, in the yellow graph, because it isn't between groups. So I guess the idea is, well, we'd have the group of U and the group of V, which we very graciously created earlier. So we have the group of U, which is the group of U, and the group of V, which is the group of V. Now, if group of U doesn't equal group of V, right? If they're not in the same group, that means that what? That means that in our hypergraph, U append V, right? Which is the same idea here, right? We have a hypergraph where 6 has to come before 1. So then in the hypergraph, G of 0 has an edge going to G of 1. Okay? So that's how you populate that hypergraph. And then let's run topological sort on the hypergraph. And again, it's only going to consider those yellow nodes. It's not going to think about what's happening inside. So we have a group graph. And how many nodes are there? Well, there's M nodes. And let's print the group ordered, just to get an idea if this works for that as well.